Okay, Luke, you should have presenter status now, and maybe wait another minute or two to make sure the YouTube live stream is going and everything. By the way, it's good to see some UW folks participating in the conference. You're right down the street, some local folks. It's always good to see. Yeah, let's just wait or two. Oh, Daniel says that YouTube live is ready. So Luke, you can go. Please begin. Luke, we can't hear your audio.
Testing, can you hear me now?
Yes, we can hear you.
Okay, perfect. Let me get back to the, all right, okay, I think we should be back. There we go. My webcam doesn't seem to be coming through, but it says it's a permission error on, let me try stop and share. Webcam sharing locked. I'm not sure what that, oh, there we go. Okay, perfect. So, hi, my name is Luke Nelson. Today I'm going to tell you about how we used formal verification techniques to help eliminate bugs in the BPF JITs that are in the Linux kernel. And this is work that I did together with several other people at UW. So, as we've seen throughout this week, there's BPF is used for many important parts of the kernel. So, it's been used for tracing and networking and security and other important purposes. And the basic way that this works in Linux is that user space downloads a BPF program in BPF bytecode into the Linux kernel. The Linux kernel has a component called the verifier that checks that the BPF program is safe. And then if it is safe, it sends it to a BPF JIT compiler, which compiles it to native code for better performance. So one problem that exists with these BPF JIT compilers is that they can be very difficult to get right. And the main reason behind this is because when you're writing a BPF JIT compiler, you have to think about code that's executing at multiple different levels. And what I mean by that is that you have to think about the code that's executing in the JIT itself, as well as the machine code that's being produced by the JIT. So the kernel has existing self-tests and fuzzing techniques, and these can be effective at preventing many of the types of bugs that can happen in BPF JITs. But the search space is just too big to exhaust all the possibilities. So there could be many corner cases lurking, both in the input to the JIT and to the input to the BPF program itself. And because the compiled code runs directly in the kernel, any bugs in the JIT might be able to be exploited by some malicious BPF program to become a kernel security vulnerability. So to make it a little bit more concrete why these BPF JITs are hard, here's a little snippet of the 32-bit x86 JIT for the BPF instruction that loads a 4-byte value from memory. And the thing to note here first is that there can be control flow in the BPF JIT itself. So the mapping from BPF instructions to native instructions is not just one-to-one. Often the JIT is doing some complicated logic to determine what instructions to produce. And then secondly, in some examples, the generated code itself also has branches that you have to think about. So the second thing is that in some of these JITs, like at least the x86 JITs, they're emitting native instructions as these raw bytes with these emit functions. And so that means is to understand what this code is doing, if you're reading or writing it, you have to sort of keep an x86 decoder in your head, which is quite a feat. So there's actually at least one bug in this code. And it's quite difficult to be able to spot what the bug is. And so what we need is some way of systematically testing this code that would be able to catch all of the bugs and verify that we've correctly fixed them. So one promising approach is called formal verification for doing this. And the idea behind formal verification is that you're going to formally prove that the piece of software that you write is free of bugs. And the basic way that you do that is first you come up with a specification. So a specification is an abstract description of what the intended behavior of the code is. And ideally, your specification is smaller and therefore easier to audit than your implementation. And then you'll prove that your implementation satisfies your abstract specification. And so what this would show is that your implementation at least doesn't have any more bugs than what the specification has. So, but not everything comes for free. and formal verification especially, comes with a cost, and this cost is largely the developer burden. So to do formal verification requires a lot more effort on the part of the developer compared to other techniques such as testing. And this effort comes largely from two different places. So first is when you're, if you want to apply formal verification, you have to actually sit down and think of what the specification for your code should be. And this is difficult for a number of reasons. So your specification has to be restrictive enough to prevent the bugs that can occur in your code, but it also has to be general enough to cover the existing implementations that you're trying to verify, such as the BPF JITs that are in Linux. Secondly, once you've decided what your specification for your system should be, you have to prove that your implementation satisfies that specification. Manually writing these proofs can be very time consuming. So oftentimes for manual proofs, there can be more than 10 times the number of lines of code of proof compared to implementation. Now, there is also this idea of automated formal verification that doesn't require you to write any manual proofs, but it's not clear that these techniques will trivially scale well to the problem of BPF JIT verification. So today what I'm going to tell you about is a tool that we built called Jitterbug. And Jitterbug is a tool that does automated formal verification for the BPF JITs in Linux. And there's two main new things in Jitterbug. So the first is that Jitterbug comes with a specification of BPF JIT correctness that rules out the types of bugs that we see in BPF JITs and is also amenable to the existing JIT implementations in the kernel. And second, Jitterbug comes with an automated proof strategy that liberates the developer from having to write any manual proofs, and again, works for the implementations that are in Linux. And the implementations for these JITs are actually, we write them in a domain-specific language that Jitterbug introduces, specifically designed for verifying and implementing BPF JITs. So our main results are that using Jitterbug, we found and fixed more than 30 new bugs in existing BPF JITs in Linux across 11 patches. And to do this, we manually translated the C code of these JITs to our DSL for verification. This process took roughly several weeks per JIT. Secondly, using Jitterbug, we developed a new BPF JIT for RISC-V 32, or 32-bit RISC-V, which there previously wasn't a BPF JIT for. And to do this, we first wrote our JIT implementation in the DSL that Jitterbug has, and then we wrote a tool to do automated extraction to C code. And this automatically extracted C code is what's in the Linux kernel today. And then lastly, we used Jitterbug to develop and verify 12 new optimization patches for existing JITs. So now I'll give you a brief outline of the rest of the things that I'm going to talk about in this talk. So first, I'll give an overview of how you should think about how the BPF JITs in Linux work. Then I'll talk about a case study of bugs that we've seen in BPF JITs in the past, and an example of some bugs that Jitterbug has found. Then I'll talk about Jitterbug's JIT specification and how it rules out the types of bugs that we studied in the case study. Then I'll talk about how to use Jitterbug. So it's the basics of how Jitterbug works and what developers have to provide in order to use it. Then verification effort, so how hard it is to actually prove these BPF JITs correct. And then lastly, a short demonstration. And then I'll talk about some future directions for JIT verification in Linux. Okay, so starting off, give an overview of how the BPF JITs in Linux work. So sort of reiterating what we saw earlier, the BPF JIT works by passing a BPF program to a verifier, which passes it to the JIT compiler, which compiles it to native code. The key thing about this for Jitterbug is that we're just focused on the correctness of the BPF JIT. And so for now, we're assuming that the BPF verifier is correct. So the JIT compiler is allowed to trust that the program that it's compiling has already passed the BPF verifier. So what exactly do these BPF JIT compilers look like? Well, you can think of a JIT compiler as consisting of roughly 3 parts that I've shown here on the right. So first, the JIT has this emit prolog. So that produces a native function prolog that can save the call save registers and set up the BPF stack and do other initialization, things like that. The second thing the JIT does is for each BPF instruction, it compiles it to some sequence of native instructions. And it does this separately for each individual BPF instruction. So one BPF instruction at a time. Then at the end, it emits some epilogue that does cleanup of the BPF stack and setting of the return values, etc. So some other things to note about these BPF JITs. First is that they do static register allocation. So they map each BPF registers to some fixed piece of hardware state, such as a hardware register. They compile one BPF instruction at a time, and Another feature of them is that because they have to compile BPF jump offsets into the corresponding native offsets, it actually has to repeat the JIT process until the generated image has converged. Okay, so now we've seen what these BPF JITs look like. So what sort of things can go wrong when people are developing these BPF JITs? So first, some background on the BPF JITs and sort of their history in Linux. So what I've been calling BPF is actually eBPF, or extended BPF. And JIT support for various architectures for eBPF has been added roughly over the previous 7 years. So here's a timeline of the past 7 years and what year the architecture, the JIT for each architecture was first introduced. So for our case study, we just looked at the JITs for x86, ARM, and RISC-V, the 32 and 64-bit variants of each for 6 architectures. So for these 6 architectures, we manually went through all of the bug fixing commits for these existing BPF JITs. What we found is that there were a total of 82 JIT correctness bugs across 41 commits during that time period that they were being developed. And here we counted a correctness bug is the JIT produces wrong native code for a single BPF instruction. So a single commit might fix multiple bugs. What we did then is categorize these bugs by the type of BPF instruction that the bug affects. So we were curious what types of instructions tend to be affected by bugs the most. And what we found is that these bugs have occurred across all different types of BPF instructions. So 33, or just over a third or so of them have been involved in ALU, or arithmetic instructions, but we also see them across other types of instructions like memory, jumps, calls, and prologue and epilogue. So of these 41 bug fixing commits that we looked at, 11 of them were bugs that we fixed because we found them by applying verification using Jitterbug. And these are across a variety of different architectures. In the interest of time, to give you an example of what bugs in BPF JITs can look like, I will show you the details of just these first 2. So the first bug I'll talk about is a bug that was present in the 64-bit RISC-V JIT. And the basic idea of what happened with this bug is that BPF 32-bit has 32-bit ALU instructions. And the semantics of the BPF 32-bit instructions are that they 0 extend the result to the 64-bit BPF register. RISC-V 64-bit also has 32-bit arithmetic instructions, but on the other hand, these ones sign extend to 64-bit. And so the bug was that this mismatch between the semantics of the BPF and RISC-V instructions meant that the JIT would compute the wrong result when the result of the arithmetic instruction was negative. So here's an example of the JIT code below that shows the bug and what introduces the fix. So this is the BPF JIT for 64 and 32-bit subtraction. It either emits a RISC-V subtract instruction or a 32-bit subtraction instruction, the sub W. And then the fix for the bug is to add an additional check. If it's not a 64-bit instruction, then emit 2 extra instructions that 0 extend the upper bits. So this is an example of a bug where there's a semantic mismatch between the intended behavior of the BPF instruction and the actual compiled code. So the second bug that I'll talk about is actually a bug that was present in that example that I showed at the beginning of the talk. So this is from the 32-bit x86 JIT. It's for the BPF instruction that loads a 4-byte value from memory. And similar to the 32-bit arithmetic instructions, the semantics of this instruction are to 0 extend the upper 32 bits. So to understand a little bit more what the bug is, you have to know that on 32-bit x86, it maps each BPF register to 2 x86 registers. And this is because BPF registers are 64-bit. So it maps a 64-bit BPF register to 2 x86 registers, one of which holds the high bits of the BPF register and one of which holds the low bits. So to 0 extend a BPF register on 32-bit x86, that means we have to set the corresponding x86 register to 0. And the instruction that the JIT tries to do to set these bits to 0 in this example is this move L of a 0 immediate into whatever the high bits of whatever register corresponds to the high bits of the destination. And the bug is that the JIT doesn't correctly encode this move immediate instruction. So to see exactly why, I'll dig into the details of this line of code. So emit 3, that's just a macro that emits 3 bytes of raw x86 instruction. So the first byte is a C7. That's just the opcode for moving a 32-bit immediate into a destination register, and that's fine. The second is this add_1 reg. this is a byte that encodes the destination register. If you're familiar with x86 encoding, this is the mod r/m byte. And the last byte, this 0, is 1 byte of the immediate. So the bug is that this x86 instruction expects there to be 4 bytes of immediate at the end of the instruction, but the JIT only encodes 1 byte of immediate, this first 0. So what will happen if you try and execute this code is that the first 3 bytes of whatever instruction follows this in memory will be swallowed as the immediate, and then that will break the entire stream of x86 instruction, which isn't great. So the fix that we did was to use an XOR of the register with itself instead. This uses the correct encoding. Uses only 2 bytes instead of 6 that are required for the correct move immediate, and it's actually the canonical way of clearing a register on x86. Okay, so we've seen some examples of bugs that can happen in BPF JITs. So next, let's see how we can write a specification that can rule out these types of bugs. The main question is, how do we write down a spec that systematically rules out various different types of bugs that can occur in BPF JITs? So we want to rule out encoding bugs like the one that we saw in x86, as well as semantics bugs like the one we saw in RISC-V, as well as others. And we want to rule them out for a variety of BPF instruction types. And the main questions here are, first, what does JIT correctness even mean in this context? And second is, how do we prove that the implementation meets the specification that we've written down? So the high-level picture of the specification that Jitterbug uses is this property that we call end-to-end correctness. And what this says is that for any possible valid BPF program, if you compile that BPF program down to some native instructions, so a compiled program, and then you provide the same input to the BPF program and to the compiled program, then they should produce the same output. That is, they should produce the same return value, and then they should also produce the same trace of events. So that's the sequence of memory loads and stores or function calls to the kernel that the program performed. So basically anything that's externally visible. And the nice thing about this spec is that it's very abstract. It doesn't talk about the details of individual BPF instructions or anything like that. You can convince yourself that a JIT that satisfies this property is correctly compiling BPF programs. But the thing that's difficult about this is that it's quite hard to prove this, directly at least, because we can't enumerate all BPF programs. Or even if we could, it would probably take an extremely, extremely long time. So what Jitterbug does instead is breaks down this end-to-end correctness property into 3 different parts that together imply the end-to-end correctness. So the first part is this thing called prologue correctness. And all this says is that the JIT prologue correctly sets up the BPF state. So it correctly sets up the BPF stack, and it correctly saves in callee save registers. The second part is what we call per instruction correctness. And that means for any individual single BPF instruction, the JIT will produce the correct machine code. And then lastly, we have epilogue correctness. So that's that the JIT epilogue tears down the BPF state correctly and sets the return value. So this is still very abstract. So let me tell you exactly what I mean by the per instruction correctness. So per instruction correctness, what you can think of it as doing is exploiting the per instruction nature of the JIT compilers. So recall that the JIT compilers compile BPF programs 1 instruction at a time. So it follows that we would want to reason about these BPF JIT compilers 1 BPF instruction at a time. So what per instruction correctness says is that if you have some arbitrary BPF program state and some arbitrary native machine code state, and those states are related in some way, and I'll describe what I mean by related later on. But if they're related in some way, and you execute the BPF instruction, and you execute the result of the JIT on that instruction, so the compiled instructions, you should produce 2 states which are again related. So this idea is nicer than the end-to-end correctness one, because we only have to reason about a single BPF instruction at a time, which we definitely can is simpler to reason about. But even this hides a lot of the complexity that is actually involved with trying to prove BPF JIT correctness. So there's several things that make JIT correctness hard in the context of the JITs in the Linux kernel. So first is that the JIT itself can contain branches. So here on the right is another snippet from the 32-bit x86 JIT for storing a value to memory. And just in this one example, for this one instruction, there's at least 7 different branches in the JIT code, in the JIT itself. And so that means there's many possible paths through this code to consider. And the JIT should be correct for all possible paths through this code that get taken. And the number of paths can grow quite quickly, since the number of paths in general is going to be exponential in the number of branches. So this makes it complex to verify the BPF JITs. The second thing that makes JIT correctness hard is that the JIT can produce code that the native code itself contains branches. So this is an example on the right for the 32-bit RISC-V JIT for a 64-bit left shift by a register. So the things to note here are that this code that it generates actually has branches. You don't have to understand exactly what the branches are doing, but the high-level idea is that it's branching on the amount of that it has to shift by so that it can emulate 64-bit shifts using 32-bit hardware. And similarly to the branches in the JIT, this code should be correct for all possible paths through the generated code. So for all possible sequence of jumps that you take. And this complexity sort of stacks on top of the complexity introduced by the branches in the JIT itself. So lastly, is we actually have to say what we mean by this when we say that the BPF and the native states are related. So we need some way of mapping the BPF state onto the machine state. And in Jitterbug, we break this down into roughly three components. So the first is how to map BPF registers onto hardware. For some architectures, this mapping is simple. It's just a one-to-one BPF registers to hardware registers. But in some architectures, like 32-bit architectures, each BPF register might have to map to multiple target registers. Or if there aren't even enough of those, it might have to map to locations on the stack that are loaded and saved to temporaries as needed. So that makes it difficult to specify the register mapping. Second, in order to know that we've compiled BPF jump instructions correctly, we have to have some way of mapping the BPF program counter onto the program counter of the native machine. And this is difficult because each BPF instruction can be compiled to a variable number of target instructions. So this mapping from BPF program counter to machine program counter isn't just some scale and offset. It's nonlinear, and so we have to have some way of specifying that too. And lastly, we have to specify how the BPF memory maps onto actual memory for the native code. And this is difficult because BPF programs can have variable stack sizes, and the JIT should be correct regardless of what the stack size is. And the BPF JIT stack should not overlap with any stack locations used by the JIT. So the BPF has a stack itself, and the JIT has a stack, and those regions have to be disjoint. Okay, so now we've seen an overview of Jitterbug's JIT specification and why it's hard. So now I'll show how developers actually use Jitterbug and what developers have to provide in order to use it. So this is the high-level overview of how Jitterbug proves JIT correctness. So it starts at this top left BPF instruction. It starts with a symbolic BPF instruction, which you can think about as representing any possible arbitrary BPF instruction. The next thing that Jitterbug does is it does a process called symbolic evaluation on the implementation of the JIT to produce a set of symbolic machine instructions. So you can think of what this is doing as exploring all paths of the JIT implementation and coming up with a set of all the possible machine instructions that the BPF JIT could generate. So now we have a symbolic BPF instruction and a corresponding set of possible machine instructions that are compiled for that instruction. The next thing we do is run symbolic evaluation of a BPF interpreter on the BPF instruction. And what this does is reduces the BPF instruction to a set of logical constraints that represent the semantics of the BPF instruction. Similarly, we symbolically evaluate a machine interpreter on a set of machine instructions that we obtain from the JIT. So what we end up with now is two formulations. So we have a logical formula representing the semantics of the BPF instruction, and we have a formula representing the semantics of the machine instructions. So we feed them into our functional correctness, so our per instruction correctness definition, and ask an SMT solver to prove that they're equivalent. So in order to use this whole process, what does a JIT developer actually have to provide? So they have to provide these things that are in these shaded boxes. It's 4 different things. So the first is that they have to provide an implementation of the JIT in Jitterbug's DSL. Second, they have to provide a symbolic interpreter for the machine instructions for the architecture that the JIT is targeting. Third, they have to provide that architecture-specific state mapping that I described earlier. And then lastly, they can provide any additional architecture-specific invariants that they might have. So things that don't have to do specifically with BPF, but need to be maintained anyways, like stack alignment. So I'll show you the details of what these first 3 actually look like. So first is the JIT implementation. So as I said earlier, Jitterbug introduces a domain-specific language for implementing and verifying BPF JITs. So it's a subset of the Rosette programming language with a one-to-one mapping to C code. And Rosette is a programming language that makes it easy to write symbolic reasoning tools. And the reason we choose this is because it allows us to have finer grained control over the symbolic evaluation process, which helps us scale the verification to that to actually work. For the new RISC-V 32-bit JIT, we do automated extraction from the DSL to the C code that's in Linux. And for existing JITs, we have to manually translate from the C code to the DSL for verification. And as future work, we'd like to be able to reason about the C code directly without having to do this manual translation work. But for now, we still manually translate them. So here's an example of what the code actually looks like. So here's a snippet from the RISC-V 32-bit JIT. On the left is the DSL code. So Rosette is built at bracket, and bracket is a dialect of Lisp. And so that's where all of these parentheses and brackets come from. But the thing to note is that this mapping is largely one-to-one with the C code. So you can see this is the code for 64-bit shift on RISC-V. And the code looks slightly different, but the mapping from C code to DSL is actually fairly straightforward. So for this example, for the 32-bit RISC-V JIT, we wrote the code on the right and verified that it was correct, and then used our tool to automatically extract it into the code on the right. For existing JITs, we have to sort of manually do the reverse process of starting with the C code and then porting it ourselves back into the DSL. The second thing that BPF JIT developer has to provide is a machine interpreter for the instructions that the JIT targets. And this is so that Jitterbug knows the semantics of the machine instructions that are produced by the JIT. So to do that, you have to write an interpreter for the machine instructions in Rosette, and then Rosette automatically lifts it to work on symbolic instructions. So as an example of what that looks like, here's a snippet of the machine interpreter for the RISC-V architecture for the add instruction. So we start by defining a struct CPU that holds all the relevant RISC-V CPU state, such as a program counter and some general purpose registers. We define this function for interpreting an add instruction. It takes a CPU, a destination register, and 2 source registers, and it sets the destination general purpose register to the result of the sum of the 2 source registers, and then skips to the next instruction. To interpret a whole program, we obtain the current program counter, fetch the instruction at the program counter from the program, and then condition off of what type of instruction it is. So if it's an add instruction, we can call the interpret add function we defined above. And to scale this to work for an entire ISA, you simply repeat this process for every possible instruction. So that's what machine interpreters look like in Jitterbug. Lastly, the developer has to provide a state mapping from the BPF state to the target state. So this comprises registers, program counter, and memory. So as an example, for the RISC-V 32 registers, each BPF register has to map to 2 RISC-V registers or to a spilled register region on the stack. So here's a little visual diagram which represents the state mapping that's used by the RISC-V 32 JIT. So on the top here is the set of BPF registers, and on the bottom is the set of RISC-V registers used by the JIT, as well as a little diagram representing the stack layout during JIT execution. So commonly used BPF registers like R0 through R5, each are mapped to 2 32-bit RISC-V registers, one of which holds the high bits of the BPF register and one of which holds the low bits. Other BPF registers are mapped to a special designated region on the stack that holds their values, and then those are loaded and saved to temporaries as needed. So in order to use Jitterbug, the developer has to specify exactly what this mapping is in order for the code to be verified. So I've talked a little bit about using Jitterbug to find bugs, but we've also used Jitterbug for other purposes in finding bugs. So for example, we've developed and verified the new JIT for RISC-V 32 that I described. We've also developed and verified optimizations for existing JITs. So here's a list of some of the optimizations that we've developed, but in the interest of time, I'll leave it to you to see the links or ask questions afterwards to hear the details about these optimizations. Okay, so next I'll talk about the verification effort of developing Jitterbug and importing and verifying the JITs. So Jitterbug itself is roughly 2,200 lines of Rosette code. This is excluding the machine interpreters and any architecture-specific specifications. So this is just the core libraries and core specifications that Jitterbug defines. The RISC-V 32-JIT, we co-developed it with Jitterbug over the course of about 10 months of development, and the RISC-V 32-bit is since been shipped with Linux 5.7. We developed the JIT specification and the proof technique together with the RISC-V 32-JIT. And then once we were sure that it was reasonably stable, porting the other architectures to use the same spec and proof technique took roughly several weeks each. And the JIT optimizations took roughly several weeks each as well, between writing the optimization and interacting with kernel maintainers, etc. So here I've shown some lines of code that represent the JIT verification effort. So for each architecture, I show the lines of code of the implementation for the C and the DSL, as well as the lines of code of the specification. So the JIT specific specification, as well as the machine interpreter. So the main effort in verifying these JITs is actually in writing the machine interpreter, which is makes sense because there's lots of different types of instructions that you have to handle in the machine interpreter. The effort to port the DSL from to the DSL from the C code and to write the JIT specific specification is relatively small. This is roughly 3 weeks each, but there's added effort to keep the DSL code in sync with the C code. So it's still sort of annoying to have to keep this to have to keep the DSL code around, but for now it's necessary in order to do the verification. So secondly is about the verification performance. So here what I've shown is for each architecture, the verification time that it takes to verify a single BPF instruction, a single opcode class of a BPF instruction. And the verification time is usually less than 1 minute for one instruction, which means you can get rapid feedback if you're developing a new optimization or fixing a bug or developing a new JIT. So that makes it easy to actually use verification. Okay, so next I'll show a quick demo if I could figure out how to share my screen. Let's see. Actions. Does anybody know where the share? Oh, here we go. Sorry. Entire screen. Okay, I believe my screen should be up now. Someone should tell me if it's not.
It's visible.
Perfect. All right. Okay, so let me show you this example. So what I'm going to demonstrate in this demo is how Jitterbug finds the JIT bug that I described earlier, and that was found in the 64-bit RISC-V JIT. So the one that was with subtraction and the 0 extension. So here on the left, I'm showing is the C code that corresponds to that instruction. It's very similar to what I showed earlier in the slides. So it emits either a RISC-V subtract or subtract 32-bit instruction. And then this is actually the fixed code. It also admits a 0 extension if it's a 32-bit instruction. So on the right here is a corresponding DSL code that we manually ported. And it's a 1-to-1 translation between the C code and the DSL. So it's the same set of instructions. It does the same things. So to test the verification for Jitterbug, I'll actually go ahead and comment out the bug fix in order to artificially inject the bug and see if Jitterbug is able to catch it. So I've commented out the bug. Let's go over here. So what I'm going to do is ask Jitterbug to verify the BPF JIT for this particular opcode. And what that means is it's going to try and prove that for all possible destination registers, and for all possible source registers, and for all possible values of those registers, that the JIT is correct. It actually comes back and says that there has been a test failure, which is good because we injected the bug. So I'm glad it didn't accept it as correct. And what Jitterbug tells us is a bunch of information that might help us debug what exactly went wrong. So when verification fails, Jitterbug comes back with a concrete test case that you can use to figure out what exactly the bug is. So what Jitterbug tells us, here it says, first, the BPF JIT specification, the final registers must match. That means that the JITted code and the BPF instruction disagree on the value of some register for this instruction. So the BPF instruction that's involved, that it comes up with is an ALU, so 32-bit arithmetic, subtraction BPFX, so subtract a register, between R9 and R10. So it wants to subtract the value in R9 or in R10 from R9. And these are the BPF offset and immediate fields, which aren't used for this instruction, so they're just 0. It will also tell us what the corresponding RISC-V instruction is. So it says it's using a sub W, And then it has some encoded RISC-V registers corresponding to the BPF registers. So what's actually really useful in helping diagnose what this bug is these next following things. So first, it'll tell us what the initial value of the BPF destination and source should be in order to demonstrate what the bug is. So what Jitterbug is saying is, suppose that initially R9 holds this value right here, this FFF 7FFFE. And then suppose that R10 holds this value FFF 7FFFF. If we interpret the correct BPF semantics, the result in R9 should be this. So if you subtract these two using 32-bit arithmetic, you get -1. And then if you zero extend that to 64 bits, you get -1 in the first 32 bits, and then all zeros in the upper 32 bits. So this is the correct value that should be computed. And what Jitterbug tells us is that for the JITted code, this is the value that it finds in that register. It actually finds all ones. So this is actually can tell us that an idea of what's happening is that we're sign extending this value instead of zero extending it like we should. So this is an example of how, and if this was a real bug, you could go and write a new Linux kernel like self-test that sets up the registers in these values to catch and demonstrate that it is actually a real bug and prevent it from regressing in the future. So next, I'll uncomment the bug, or uncomment the bug fix, and then go back and ask Jitterbug to verify it again. Let's see what it says. Hopefully it accepts it this time. Usually it takes about 6 seconds or so to finish solving. Great, so it tells us that it actually successfully verified it. And what that means is that this particular part of the JIT code is correct for all possible destination, source registers, and initial values. So then we can move on to verifying the JIT for other different types of BPF instruction opcodes until we've done them all. Okay, so that's the end of my my short demo. Next, last thing I'll talk about is some future possible directions for JIT verification in Linux. So currently, we have to manually translate the C code that's in Linux into the Jitterbug's DSL for verification. And this is quite hard to maintain, especially because the C code can be changing. And so we have to maintain this mapping from the C code back into the DSL code. And ideally, we want JIT developers to be able to verify the C code directly without needing to know how to write Rosette code. And there's two main barriers to achieving this. First is we need additional research on scaling automated verification and symbolic evaluation of C code. And that's something that I'm still working on. Secondly, is we need a common JIT interface in the kernel that's amenable to the specification that we can actually plug the verification into. So to tell you exactly what I mean by that, I'll describe an experience that we had when we were developing the RISC-V 32-bit JIT. So when we first started developing the RISC-V 32 JIT, the sort of top-level interface to the BPF JIT looked like this BPF int JIT compile function that takes a whole BPF program and compiles it to a whole native function, so it does the whole thing. And this is kind of hard to use for verification for the same reason that the end-to-end correctness that I described earlier is hard to directly prove. So during the process of development, we actually factored this function with from the 64 and 32-bit RISC-V JITs to actually be shared between them. So now the top-level interface that each architecture has to provide is these three functions. So build prologue, emit one instruction, and then build the epilogue. And what's nice about this is a couple things. First, this actually mirrors the breakdown of the specification that Jitterbug uses into the prologue correctness, the per instruction correctness, and the epilogue correctness. And then also it means there's less code to maintain in Linux because there's no duplication between the 64 and 32-bit RISC-V JITs. And one thing that we think might be useful in the future is thinking if it's possible to factor this code across even other architectures at some point, so that not every JIT has to re-implement roughly the same logic for building the body of the JIT function, et cetera. And so that might make life easier if it's possible, that might make life easier for maintainers and also easier to do the verification in a more automated way. So the last thing that I'll talk about is sort of what's next, what things might we want to look at in the future. And one thing is the BPF verifier that I showed earlier. So far we've been trusting the BPF verifier to be correct, which sort of simplifies the life of the BPF JIT. But the BPF verifier itself is also hard to get right. And it's hard for, there's a couple sort of symptoms of this. So first is that sometimes the verifier accepts code that it should actually reject. And an example of this is that safety bugs have been found in the verifier in the past. The second thing is that a lot of the time verifier rejects code that is actually safe, that it should accept. And it can be very hard to actually get the verifier to accept a BPF program, especially when you have complex interactions with LLVM. So it's possible you write some C code, compile it to BPF. It can be hard to make sure that it's in the right shape that it'll be accepted by the BPF verifier. So we haven't done anything on this yet, but it could be interesting in the future to do more research on how to develop BPF verifiers that accept additional safe programs to make developer of BPF programs' lives easier, but still rejecting the unsafe ones. So that could be interesting line of future research. So lastly, I'll conclude by saying that Jitterbug is a tool that we built that allows developers to do automated verification of BPF JITs. And our experience has been effective at finding bugs in existing JITs, as well as developing new JITs and new optimizations. And ideally, after we've sort of, sometime in the future, it'll be integrated into the BPF JIT development process. So all of our code is publicly available on GitHub, and I'd like to acknowledge all of these people for being kind enough to review all of our patches to Linux. So thank you. And I will take any questions that people have.
So if it's you have some questions for Luke, then that's a good time to ask. I actually have a quick question. One interesting class of bugs that I've actually had to fix involve branch offsets being not encoded correctly, and contextually, this is whether the bug triggers or not depends upon the context of the totality of the BPF program, such as the total size of the BPF program can cause the branches to be encoded incorrectly or whatever. Is Jitterbug able to evaluate and validate these kind of bugs?
Yes, I believe so. So Jitterbug, when it's verifying the per instruction correctness, it doesn't make any assumptions on the actual total size of the BPF program. It assumes it could be anything. And it assumes that the context offset mapping, the mapping from BPF instruction to like native offset, it assumes that mapping could be anything as well. So in order to show that a BPF jump instruction is correct, it actually has to be correct for any valid mapping from BPF to target instructions. And so we've used this to actually find some existing BPF JIT bugs in jump instructions. So similar bugs to the ones that you described. Yeah.
I see. That's great. So logically, it's testing the branch for all possible initial PC values.
Yes. Yep.
Cool. Paul Chagnon says, thanks, great presentation. You mentioned a couple of times that Jitterbug assumes the BPF verifier is correct. What does that mean in practice? What could be the impact if the verifier has a bug?
Yeah, so far we haven't done any verification of the BPF verifier itself. So if the BPF verifier has a bug, it might let an unsafe BPF program through, and then sort of all bets are off for what the JIT is going to be able to do. So the BPF JIT Jitterbug is sort of really focused on the correctness of the BPF JITs and not looking at the BPF verifier itself. But it could be interesting to also look at that in the future, since I know that sort of historically that's been somewhere where bugs have also shown up.
Cool. Some people are typing, so let's wait for them to finish. Will Deacon says, that was fascinating. Thank you for the RISC-V 32-bit JIT, which is generated from Rosette. Is the C source code still patched upstream, or is the Rosette patched and the JIT regenerated instead? If the former, what steps are taken to avoid regressions?
Yeah, so the thing about the RISC-V 32 JIT that lets us do this is, for now, that we're actually maintaining the RISC-V 32 JIT. So any changes that we can make to the DSL and then regenerate the C code. It's actually unclear because we have to do this porting process for the existing JITs. That's why we're trying to get the tool to work directly on the C code so we can sort of skip this porting process. It would be nice in the future to be able to let other people use this, and so that we don't have to maintain all of these Rosette copies of the BPF JITs. For now, that's as good. That's the best we can do, but we're working on it.
Great. Daniel Borkman says, awesome work, Luke. When do you plan to upstream this work into the kernel? It would be useful to have the specs maintained alongside the JITs in the tree so that when people extend JITs with new instructions, they can also extend the RKT code alongside with it and verify the instruction. Actually, that's a very good question, whether this makes sense to do something like that.
Yeah, so currently my sort of litmus test for when I think it's reasonable to actually upstream this would be once it's possible for people to run and maintain at least parts of the BPF JITs without having to understand the rosette. Because it's sort of I feel like it's a big burden to have people, in addition to changing the C code, understand the rosette code and understand the tools of how to do this verification. But once we're able to verify at least parts of the C code directly, without requiring this manual reporting process, then in my mind, it would be useful enough for other developers who aren't us to use it without having to understand the details of the racket code. But also, if it seems reasonable to upload or to upstream the racket specs earlier than that, then we don't have any opposition to it. We just want to make sure that it's the most it's as useful as it can be without introducing any additional overhead on JIT developers' workflows.
Yeah, if that ever occurred, there would be the question of what requirements would exist for making sure that the DSL and the C code are in sync.
Yeah, exactly. That's the main. It's already hard enough to make changes to the JITs. It's probably also hard to ask people to maintain two different copies of the thing.
Right. There's some people typing. Daniel says, makes sense. Thanks a lot. Do you also plan to check out some of the other architectures that haven't been mentioned here, for example, S390 and Smart?
We don't have any plans to do that yet, but we definitely could in the future if people think that would be a useful place to look for bugs.
Okay, a couple people are typing. Let's see what they have to say. We're about up on the hour, so I think these will be the last questions for sure.
All right.
Daniel Axton says, I work on PowerPC 64. We're going to have a look at your code and get in touch. So that's great.
Cool. Thanks.
And John Fastavan seems to be the last person typing. Oh, and come on, folks. At the end of the session. Oh, John says, in the future directions, would Jitterbug be useful for the verifier as well, or would you imagine that to be some other tools?
Yeah, so for now, a lot of the techniques that Jitterbug uses, it's not clear how they would scale to be able to work for the BPF verifier itself. The BPF verifier is a much more complex property because it sort of depends on the entire BPF program. Like you have to, it has to keep track of state of the entire BPF program to know that if it's safe. It's a lot harder to break it down into this per instruction correctness. And so we have some ideas of ways of developing the verifier that might be effective, but it's not clear at least that Jitterbug will be applicable to it, or even that verification might not even be the right approach to the right trade-off for mitigating bugs. So we're still actively thinking about that. Oh, and as far as S390, yeah, that could be interesting to take a look in the future.
Yeah, Serhii Makarov says the S390X is a sweet spot where the demand for it outstrips the engineering time, and that's a good point about whether this could make it easier to maintain it and verify a JIT if there's not a lot of engineering resources available. So that's a great
right.
point. Okay, Luke, thank you very much for your presentation.
Thank you.
This looks like awesome work, and I wish you luck in the future.
Thanks.
Okay, so moving on, I'll take the presenter back and set up the next talk. Martin. Okay, Martin, I've given you presenter status. You should be able to manage the slides and begin your presentation whenever you're ready.
Yes, let me try to start my webcam. Okay. Hi, everybody. Thanks for joining in. My name is Martin. I work in the kernel team in Facebook. Today, I want to talk about the BPF work we have done in the networking stack. So in 2015, I attended the LPC. So one of the topics that got brought up was the protocol ossification. So in our team, we always got questions asked like, how easy is it to test or deploy a new TCP congestion control idea? The answer is usually discouraging because it turns out to be how easy is it to make kernel changes without the kernel panic, and sometimes it's also very difficult to deploy those changes. It will be like, how quick is it to upgrade the kernel, or at least to upgrade the kernel module? Sometimes it's not easy because some of the environment has a very long tail of kernel versions. So all of this is pretty discouraging for the networking expert or protocol expert who want to try to experiment new congestion control idea or other protocol improvement idea. So at that time, one question was asked is, can TCP congestion control be written in BPF? At that time, it was something that unheard of, and it was pretty hard to imagine how that could be done in BPF. But now actually we could do that. We can write TCP congestion control in BPF, and actually we can do more than that. So today I want to talk about, of course, the congestion control, and also about the another thing I want to talk about is the writing TCP header option in BPF. And the last thing I want to touch base also is about the socket local storage. So first, congestion control. So in this slide, I put two pieces of code. One is a BPF cubic. So both of them is cubic implementation. One of them is written in BPF, and another one is the kernel cubic. So which one do you guess is the BPF cubic here? So this one is maybe easier. The left hand side one is the BPF cubic. I think the void pointer casting may be giving this one away. So let's dive into one of the pointer implementation. The one that I picked is the SS trash because it's small enough to put it in a slide. So let's dive into the SS trash implementation. So again, here is two pieces of code. One is the BPF cubic implementation of the SS trash. Another one is the kernel cubic. From this, can we tell which one is the BPF cubic here? I think this one is harder. I think, except the very first slide I cover up, every single line should be the same. But again, the left-hand side one is the BPF cubic. Only the first line, the function selector is different. The BPF one require a macro boilerplate to define the function. So we cover how it could be written, how the BPF congestion control could be written. Let's take a look at how it is used in the production. So first, we need to load the BPF cubic. So it can be done by the BPF2 struct ops subcommand, which is the very first command I place here. So BPF struct ops register BPF cubic, then you will get loaded to the kernel. But after that, everything will work the same as the kernel congestion control. We can look at it in the sysctl. In the second command, we can see the BPF cubic is already one of the available congestion control in the system. And we can also use it as a default, use the BPF cubic as the default congestion control by setting the sysctl also. So that is the third command, the last command I place here. And yes, it can be used in the sesor op too. So we can select a field specific connection to use BPF cubic. So here's some. So we run cubic and BPF cubic under the lab testo test that Larry has created. So here's the one of the performance comparison. The one I put here is the good put comparison. So we can see the performance property is pretty much the same with the kernel one. And it has to be because if you look at the BPF cubic, it's mostly line by line the same as the kernel one. So we have a lot of other graphs to show the retransmit latency, and they're pretty much all the same. So I didn't praise of them here. So before I switch topic to the TCP head option, I want to talk about struct ops, because I think a few days ago, people has been talking about if struct ops can be reused in QDIS or some other things. So struct ops is what BPF TCP congestion control build up on. So when I try to work on BPF congestion control patches, when I look at the TCP congestion ops, it is a struct and has a few pointers in it, and each pointer is doing different thing, and different congestion control just need to implement those pointer. So if we look at this pattern, struct with a kernel struct with a field function pointer, if we look at this pattern is pretty common in the kernel. The TCP congestion control ops is one of them for sure. The QDIS ops, TCP protocol, UDP protocol, and pretty much all the kernel module is using this pattern. So what I was thinking is to if we, instead of creating a specific API that only work with TCP congestion ops, so it will be a better idea to create an API that will pretty much work for all the kernel struct ops data structure. So that's what BPF struct ops comes in. So it's an API to implement function pointers in BPF. So each function pointer is actually a BPF program, which is in the type BPF pop type struct ops. So one thing about the struct ops BPF program is it doesn't have a static running context. So, but it learned the function signature from the BTF of the kernel. So what the BTF can tell us is how many, for example, how many argument is in this function pointer, and the runtime we only need to pass those arguments to the stack. So all of this could be happening because all of this recent work has been done in the BPF. For example, the BTF aware verifier, trampoline, and the core. So thanks to all the guys that work on this area that make struct ops happen. So that will be the last slide for the congestion control. So if we look at the libBPF, how libBPF load the BPF cubic is, so as I said before, each of these function pointer is actually implemented by a BPF program. So what libBPF do is load each of this BPF program and then get a file descriptor for each of them. And then it will create the TCP congestion ops object, and then initialize each function pointer to the BPF program FD, and then load this whole object, this whole TCP congestion ops object to the kernel, and then it will get registered to the networking stack as one of the congestion control available. But good news is that you don't have to use the libbpf. I imagine you should just use the BPF2 struct ops subcommand directly. Maybe in the future, we develop QDIS ops on top of struct ops, then we should be able to reuse the struct ops subcommand as is. Okay. Next, we'll switch topic to talk about the writing TCP header options in BPF. So I think we don't lack of use case to allow BPF program to write the TCP header options. For example, one use case could be we want to communicate the maximum delay ACK in the header options so that the receiver side can set low RTO. And so this will be the example I will use in the following slides to show how it could be done in the BPF program. And actually, this use case has been proposed in some of the RFC by Google also. And there are other use cases that may be quite specific to the data center internal traffic. For example, we may want to communicate the leg speed to the other side, or we may want to communicate what congestion control we prefer to use to the other side, and many other cases like that. So right now, what the BPF program can do is it can write any header option count. That means we don't restrict what it can write, but the kernel will definitely check for duplicated options and check for whether that option format is correct or not. So by allowing the BPF program to write any option count, that gives a lot of flexibility for the data center internal traffic, because that traffic won't leak out to the proper internet, so they can have better control on what they want to send. And potentially it can support newer standard option in an older kernel. So I expect this will be mostly used during the three-way handshake, but it will also work in passing or writing option in data header or pure add header or even thin packet header. So in the next two slides, I'm going to show an example on how it could be used at the server side during the three-way handshake. So on the top right-hand corner is a quick recap on how a TCP header options looks like. So the first byte is the count. So what kind of the option it is 1 byte. And the second byte is the length of the options. And then after that is whatever data this option want to carry. So the example I'm going to use is to communicate the maximum delay ACK in the header options. So I use the hexadecimal DA for the count byte. DA stands for delay ACK. So the first thing the server want to do is to write the same ACK, right? If we receive a sing, then you want to write the same ACK back. So the BPF program will get called to write the same ACK. So first, what the server would like to do is to look at the sing header to see whether the client has communicated its delay ACK options. So it called BPF low header options to look at the sing header. So that's the first step. And the second step is if the sing packet doesn't carry the delay ACK option, then that's fine. It means the client does not support this option. Then the server can just return here without writing anything back. So in the first step here, you can The BPF program can also learn if the server is currently in sync cookie mode. If it is in sync cookie mode, it can write a bit in the option to tell the client to resend the delay add option later. So assume everything is fine, then it will go to step 4, and then it will really write the its maximum delay add in the option header now. So in this example, I set it to 10 milliseconds, and then you can call the BPF store header option helper to write it into the sync add header that that is going to send out. So now in the previous slide, it write a sync add. So now the add come back. The free handshake has completed. So the new connection has established it, and the BPF program will get called again. At this time, the BPF program can look at the sync header again, which it has saved earlier, and then to get the delay add option back from the sync header in the first step. And then if it is there, then in the last step, the first step here, you can call a helper called BPF set sort op to lower its RTO based on whatever the maximum delay at the client has told the server. So the whole concept is pretty much built around two helper, the low header options and right header option. And you may want to call set sort op to change the behavior of the connection. Depends on the options you have received from the other side. Okay, so we will go to the last topic of this talk. Is about socket local storage. As we can write more and more networking function or features in BPF, it is very common that the BPF program wants to associate some data to a specific socket. For example, tomorrow I may create a new TCP congestion control algorithm and write in BPF, but I want to store a few more data points to a connection. It could be a few more round trip time samples to a socket. So how can we do it? So one way to do it is to use the hash table to a regular BPF hash table, and then use the for tuple as the key. And then the value of this table could be whatever data you want to store for this connection. So the for tuple as the key is the destination and source IP and port. So that work, and we do have program do something like that also. But the downside is the CPU lookup time could be expensive if you do it. For example, if you do this lookup for every packet you receive or you send out, and it could become a maintenance nightmare because you have to remember to remove this key when the socket is closed. If that's not handled correctly, the map could get exploded very quickly. But that's another way. A newer way to do it is called BPF socket storage. So what it does is it stores data directly at the socket itself, and the data will go away with the socket when the socket closed it. The main helper to use this to store data or to get data from the socket is called BPF socket storage get. So you still have to pass a map in it. I'll talk about that later. Why do we need a map? And for sure, you need to pass the socket pointer in it to tell the kernel which socket you want to store the data to. The lookup benchmark shows more than 50% lookup time. So that's probably something you want to use if you want to store data in the socket. And the concept has recently being repurposed and then to allow store data at other kernel objects also. For example, it has been repurposed to store data to the inode, and all this work has been done by KP from Google. So thanks for the work on that. So in the next few slides, I'm going to talk about an example on how to store data in the SK and how you can use the BPF socket get storage helper. So for example, so to store data in SK, first you need to define a map. The type of the map is called BPF map type socket storage. So the key will be the socket file descriptor, and the value is whatever you want to store in the socket. So for example, I want to store two things in the socket. One is I want to store the round trip time, some more round trip time in the socket, and another thing I want to store is the location of the remote site, like for example, East Coast, West Coast, or APAC or Europe, things like that. So because I want to store two different things, so I have to define two socket storage map. One I call map RTT, and other one I call map location. So here is a picture, a very simplified picture on how things organized in under the socket. It's a little more complicated than this in the real code, but that is the simplified version for the discussion purpose. So there's a socket for sure, and then it will point to an array of storage. And here is why the map comes in. The map has an index stored in it, so this index tells us where this data is going to be stored. For example, the location data map, the map location index is pointing to the first element of this array. So the location will be stored in the first element of this array. And the map RTT index is pointing to the second element of this array. So the RTT data will be stored in the second element here. So when I call BPF socket storage get for the very first time, I want to create that. I want to store this data store this new data to the socket. So I want to create this data. That's why I pass the get create thread as the last argument in this helper. And the first argument is the map RTT that can tell us where this RTT data should be stored to in this array. And then the second argument for sure is the socket to tell us which socket we want to store to. And then the third argument is the in ISO data, we want to store to this RTT value. If this data does not exist, so it is the very first time I call this, so it does not exist. So RTT 10 millisecond will be stored here. So and then to store the location data, we will call the helper again, but this time we will pass in the map location instead of the map RTT, because the map location will tell us where to store this location data to. So it will be the first element here in this array. So you may ask how big is this array? What if we have more data to store than the size of this array? As I said before, that's a very simplified version of what is happening. Actually, this array is a fixed size. It's 16 element, but it is only acting as a cache. So and which is backed by a linked list, as I show here. So the cache is for fast lookup time, for sure, which is obvious. Okay, so we talk about the how to use the socket local storage from the BPF program side. So how could it be used from the user space program side? Because we have the map, so we will use the map API as usual. For example, we want to update the location. We'll pass in the location map FD. But here now we don't pass in the socket pointer. We pass in the socket file descriptor because in the user space there's no socket pointer. So we pass in the socket file descriptor. And then, for example, we want to store another location. Then we pass in location is here. So the point I want to point out is the user space program need to hold a socket file descriptor. But for some shared map, for a map that's shared, other process may not have a hold to the file descriptor. So that could be a problem. And this other map also have similar situation. For example, the socket map, we use port array and a few other map also. So how to solve it? There are ideas being brought up in a few occasions. There's an ID for each socket, and that ID is the socket cookie. Maybe we can have a generic way to get the file descriptor back from the socket cookie. But how to do that is still TBD. I would love to hear idea of what we need to think about to do that, to make that happen. Okay, that will be all I have for today. Any questions or things that I can answer?
Okay, great. Let's see if anyone has any questions in the chat room. Lorenz Bauer says, can we use SK storage for internal implementation as well, i.e. store socket map state?
What do you mean by internal implementation?
Maybe he's asking if it can be accessed from the kernel side as well for making state decisions internal to the kernel.
Oh, yeah, why not? It's some data hanging in the socket, right? If you know what the data is, why not? Yeah, I don't see why.
The question would be how to represent that in the kernel internal API so you could interpret the data and find out where the indexes are and everything.
Well, it's an array, right? So if you know what is stored in this particular element of this array, yeah, you can access it. But what is in this data is described by the BTF. So I mean, you can make sense of it on what this data is storing. For example, the first 4 byte is the RTT, the second 4 byte is something else, but you still need to know what semantic is this raw data storing. So that is something you have to manage with the BPF program you have written, which store this data in the first place.
Right. Yeah, it's an interesting conflict because BPF allows you to dynamically define what this data means, whereas the kernel's kind of in a static situation and can't dynamically figure out what every BPF program is doing with this area. Joe Stringer said, I was wondering about allocation time of the SK local storage. If I follow in your slides, it's allocated on first use, which could delay first packet and affect connection establishment latency. Is that right? Could there be a way to tell the kernel to pre-allocate a socket creation time?
No, yeah, you're correct. Joe, you're correct. It's allocated in the very first time. that data is created. But the use case, the target use case is that it is created once and then get looked up many times. So that was the case that we are targeting. So that's why we didn't pre-allocate it, and we do want to get away from the pre-allocate paradigm, right? Because we don't want to fix the size and then get and then exit this pre-allocated size, and then we will get into the same problem that John has described. That we want to dynamically allocate it again. So we want to get away from it. That was the idea.
Daniel Borkman says, with respect to TCP header option, I was wondering about the interaction with GRO GSO, but it's only used for the three-way handshake and thus not applicable with respect to aggregation there, correct?
It's GRO GSO or TSO shouldn't have anything to do. It shouldn't affect the GSO or TSO or GRO because it is done in the TCP stack, right? So everything else everything GSO and TSO and GRO will work as it. I mean, imagine we want to add a new header option, maybe a new RFC becomes standard tomorrow. We want to support this option in the TCP stack natively in the kernel. It will also add this option in the TCP stack, and then we don't have to change the GSO or GRO also. So the same thing will be true for the BPF TCP header options, because it
seems that the options are only edited by the BPF helpers you've defined for example, congestion control operations and the TCP header modifications. So that's inside the kernel, and therefore the kernel helper should handle GSO properly and GRO.
The helper does help to write it to the SKB itself, but right. But it is done exactly at the same place as the kernel will write a header option. So it won't change. It won't affect the GSO at all.
Right.
Yeah.
Hey, do we have any other questions? Anyone else have anything to ask Martin? Kevin Mason is typing. Let's give him a moment. And while I'm waiting for this, there are some people in the tooling micro conference who had some BPF questions, and Elena asked me to let people know, so you could head over there later if you have the time and want to help out, answer some BPF questions over there. The tooling people would appreciate it. Kevin Mason says, very cool presentation. I can see it inspiring a lot of new ideas. That's great. Vladimir Korskov says, do you use it already in production environment?
Yeah, for the local storage, we are using it. We're using it in the environment. For the TCP congestion control, we are definitely testing some congestion control in the production also, but not in the full-blown scale. But we're testing it. But that's what it's supposed to be, right? We want to make it easy to test it in the production. So we're definitely testing some new congestion control in that space also. Yeah.
Jonathan Lemon asks, how does the BPF SK storage compare to the SK extension storage?
How does it compare to the you mean the SKB extension storage or SK extension?
I think that may be what he is referring to.
Right. SKB extension storage, I don't know. I haven't taken a deep look into it. But you mean can we extend SKB also? Maybe that will be a more controversial discussion on extending SKB, I think.
Yeah, that's an understatement. John Fasterman asks, I want to enable SK storage get from K-probe tracing side. Are there any objections to that?
Oh yeah, actually that's one of the my to-do list. If yeah, if I'll be happy if you want to take it on. Yeah. But one thing definitely we have to keep in mind is the because we cannot access the because K-probe tracing is like we don't know where it will be called away. We don't know where this SK storage get will be called away. And that I can imagine in some of the tracing, in some of the function, if we trace that and then we call SK storage get, it may not be safe. For example, if the socket is under destruction, if we trace it there, it probably won't be safe. Yeah.
John mentions that I guess we need the sock lock at least as a minimum requirement for calling the get operation.
No, probably no, because when I write this socket local storage, I have tried to avoid the cases that we need sort lock. So I've tried very hard not to use the sort lock, and it's not using sort lock at all. So I don't think that will be the concern. Yeah, but the thing is, but I'm more concerned whether it is safe to like create or delete a local storage on all the tracing point that we can hook on, so that we definitely need to audit it. So the idea is to write list some of the function we can call socket storage get. That we use some of the word that Jerry has landed to write list the dpath helper. We can definitely try to write on that to write list a few function we want to trace.
Presumably you would need some synchronization though for the first time a storage object is accessed for a socket, because you're creating the slot, you're allocating and setting up the slot that first time.
Yeah, yes, that you're correct, Dave. That we use a spin lock, but there's a different spin. There's a different lock that we don't use the sort lock is not used. It's a totally different lock.
Okay, that should solve the allocation case then.
Yeah.
Okay, John says thank you. That's great. Do we have any more questions for Martin? Looks like John Lemon is typing. He also says thank you. Great. Thanks, Martin, for your presentation. This is really interesting work. Thanks for showing us what you've been up to.
Thanks.
All right, everyone. We are in the break until 9 o'clock. A reminder again, if anyone here who is a BPF expert wants to go help out the tooling micro conference, they apparently have some BPF related questions there and they could help you out. I've also notified them of the weekly BPF office hours, and Alina will let everyone there know about that so that if they can't get their questions answered, they could attend. But once again, if you could give them a hand, that would really help. Just head on over there when you get a chance and try to give them a hand. Okay. All right. Thank you. We'll see you in half an hour. Hey everyone, we're about 5 minutes left on the break, and once that's done, we're at the top of the hour. We'll hand things over to William too, so he can talk to us about user space OBS with hardware offload and AFXDP, which should be very interesting. Kind of a follow-up to his presentation in Vancouver. Good to see how that's going. If you could click the ready button in the poll, that would be great. I can kind of get an idea of how many people in the room are sitting in front of their seats and are ready to go. Yeah, so let's get ready for the last and final presentation of the Networking and BPF Summit of LPC 2020. Okay, William, your slides are loaded. You should be able to control them now. And in a minute or two, you can begin your presentation.
Okay, thank you. Yes, I can control it.
Okay, William, you can begin whenever you're ready.
Okay, thank you. Okay, thank you. So, hello everyone, I am William Chu. Today I'm going to talk about user space OVS with hardware of flow and AFXDP. So, first I'll give some introduction about the OVS kernel module and OVS user space data path. So majorly we have 2 or 3 data paths of OVS today. And then a data path has to couple with a packet IO library, like to send and receive packet. So I'll talk about DPDK and AFXDP. These are the 2 ways to send and receive packet to the data path. And then we are thinking about using some hardware flow mechanism. Today, OVS has TC flower support and also RTE flow support. One for the DPDK use case, the other for the kernel use case. Then we'll talk about the design of this. So these are things we are trying to do is to use the user space data path with TC flower or flow and AFXDP and share some performance number. So OVS majorly has 2 components. One is in slow path, the other is at fast path. So the slow path part is majorly user space daemon called OVS vSwitch-D. So usually the SDN controller or network controller will have higher level network policies like dropping the packet or for a particular tenant apply certain network firewall rules. And then they'll convert this policy into open flow rules and program into the Open vSwitch. The OVS vSwitch-D implement the open flow protocol. So it has support like multiple table lookup, and each table will do protocol support, passing the protocol headers, applying actions to different match and action rules, and jump to another table, for example. And so for every packet coming into the OVS, so the first packet always go to the slow path. So the data path part is a cache. So in the beginning, the cache is empty. So it goes to the user space OVS, the slow path part. And then once it resolves how to handle this packet, it insert a cache into its data path so that the subsequent packet will just stay in the fast path. So this is basically how OVS achieves good performance today. So one data path is inside the Linux kernel. It's actually called openvswitch.ko. So the idea how it works is that the kernel module registers an RX hook and receive all the packets from the particular netdef. And then we apply, like pass the packet, and then we do table lookup, and then we apply actions to the packet. So this is how the OVS kernel module works. So far, it works on a variety of different Linux distributions, and it's been well tested and integrated and use other Linux kernel components. For example, today OVS kernel module use NetFilter subsystems for connection tracking, and it also share and use the Linux kernel's tunnel implementation. For example, like Geneve tunnel, VXLAN tunnel. So, however, this kernel module is well tested, but it has kernel overhead. So another OVS data path is not in kernel, but in the user space. So this is usually used by a community called OVS DPDK. So the idea is that we want to do the packet processing in user space. But first, we need to have a fast packet IO channel. So here we are using the DPDK library to send and receive, the packet from the network device and do the rest of the processing in user space, and then send it out again using DPDK library. So it's very fast because first we have a fast channel to send and receive packet, and then we also have lots of optimization in this user space data path. However, it's not very widely used because first, deploying and debugging DPDK is a little bit hard. It usually involves a lot of low-level details. It's not like Linux kernel, which has a very good abstraction, like people doesn't need to know much about the low-level details. And another case is that usually this obvious DPDK deployment is for the appliance use case. So people has dedicated server who want to optimize the performance a lot, so they deploy obvious DPDK. So the motivation of the problem we are thinking about here is that, so customer today, they deploy one of the two. So today you can run obvious kernel data path, which is stable, has a lot of feature, well tested. It shipped with all the Linux distribution, so it's good for the hypervisor or the enterprise use case. So another case is for the high performance customer who want to use DPDK user space data path. So they deploy obvious DPDK with dedicated hardware, and they have to have some DPDK knowledge to how to tune the performance to get the best numbers. So the problem is that maintaining and running two data paths is difficult. For example, today, if we implement some features in the OVS, for example, GTPU, recently we have implemented GTPU tunnel features. So this feature we implement in user space data path, but we didn't integrate into the kernel data path. So we have to maintain a list saying that, okay, this is a list and this is the features. Some features we have done in user space data path. Some feature we have done in kernel data path since whatever version. Or sometimes both features are there, but implementation are different. So sometimes the bug happens and it's pretty confusing. So what we are thinking is that, can we have just one data path implementation? Just use one for both use case, for the enterprise customer use case and for the high performance customers. So we think AFXDP or XDP might be a solution. We are still trying to experiment and building a prototype. So XDP stands for Express Data Path. Basically, you have an eBPF program, and this program runs at the very beginning of the packet receive path at the driver level. So AFXDP is a new socket type, so which allow you to send and receive packet with a very high speed. So you can write an XDP program and then have your selective logic and then send the packet to this socket, so that the kernel is bypassed, and then with the driver, a vendor's driver support, like zero copy support, you can get a very good performance, like close to the line rate of 10 gig or 25 gig. So since OVS 2.12, we have implemented the idea of AFXDP into the OVS. So the idea is that we use AFXDP socket as a way to send and receive packet. So we inject a XDP program in the driver level. So far we didn't do much. We pretty much send all the packet to the user space data path. And once OVS receives this packet, it just follows the the OVS pipeline implementation. So it was to mention that this user space data path is the same code as the data path used by the OVS DPDK. So basically, all the implementation can be shared here with OVS DPDK. So the only difference is that the way we receive packet is through AFX DP socket instead of using the OVS, instead of using DPDK library. So this is a quick performance comparison. So on the y-axis, we are measuring the packet rate, million packet per second. So this is two machines. One runs traffic generator, sending 64 byte UDP packet. The other machine runs OVS and then just do nothing but forwarding from one port to another port. So if we install one flow, for the kernel data path, it's showing like a little bit above 1 million. For the user space data path, the UD plus OVS AFX DP, so it shows much better, like close to 4 million packet per second. And here's the OVS DPDK, like running DPDK with IX3B PMD driver, shows very good, like more than 9 million packet per second. So it's OVS AFX DP is still slower than the DPDK. And here for the kernel data path, if we install 1K flow, the packet rate improve a lot to 8 million packet per second. But that's because there are more flows, and these flows are spread into different CPU cores. So there are more soft IRQ daemon processing the packet. So basically, it uses more CPU to get that get better packet rate. Also, in the case of FXDP, we also see that it's using less CPU, but usually because FXDP still runs the device driver, so usually we see that another soft IRQ daemon is also running. So it compared to OVS DPDK, it also uses more CPU CPU times. So the takeaway from this quick experiment is that today for the OVS side, the user space data path with AFX DP is the performance is much better than kernel data path, but it's still slower than the DPDK, OVS DPDK case. So what we are thinking is that for the future, we are planning to improve add more improvement to the OVS XDP, but to get better performance, we are also thinking about hardware flow. So today there are two ways to do it. So if you run OVS DPDK, which runs OVS and compile it with DPDK library, then you can use the RTE flow API provided by the DPDK. That's one way. And the other way is you use OVS kernel data path and allowing the driver running, because the driver is still running. So the TC flow, you can use the TC flower way to offload. So here we found that we want to use user space data path because it's fast. But if you use DPDK, then DPDK will unload the driver, so TC flower cannot be used here. But with AFX DP, because the driver is still there, so we can use OVS user space data path coupled with AFX DP, and also use the TC flower API to offload. So that's something we want to try, and the topic of this talk. So compare. So we want to first we want to compare these two offload mechanisms, RT flow and TC flower. So from the OVS side, OVS VSD actually just doing the policy conversion from the open flow rule to the OVS data path flow. So it will translate into its obvious flow format. And then depend on what API you want to use. So for example, if you want to use RT flow, then OVS will translate this OVS data path flow into the format that RT flow require. For example, RT flow need to set up the first how to parse the protocol and how to do the actions. And of course, in the beginning, OVS will do probing to see whether a flow can be offload into the hardware into the RT flow or not. So if not, then it will fall back into the software case. Same thing for the TC flower. So OVS will do the conversion. So convert this OVS data path flow into the format that TC flower require, and then program into the TC flower API. And the target use, so today they already support some, both API already support some hardware flow, and OVS has some feature support to program it. But the target use case we are thinking about is tunnel and the connection tracking. So simply doing 5-tuple match and action no longer meets today's firewall rule. So most of our use case has to go through 3 obvious data path flows. So for example, here, an incoming packet usually goes through first, it tries to match the outer header and then doing the tunnel decay. For example, we are using Geneva tunnel, and there are other people using VXLAN tunnel. So when we do tunnel decay, we extract the metadata and put the metadata somewhere, and then we do recirculation. And then we hit second flow. Second flow will try to match on the metadata, tunnel metadata. For example, using VNI, VXLAN ID as the tenant's ID. And then we send it to connection tracking. And connection tracking also requires recirculation. So it recirc, and then we hit the third flow. So at the third flow, we already know that, okay, this is the inner packet, and this is for a particular tenant. Then we try to match the connection tracking states. For example, whether this is a new TCP connection or it's already established. And based on the connection states, connection tracking states, we decided to forward or to drop, apply different actions. So based on this use case, we want to we have 2 requirements. So either in an environment we have a hardware that can do offload, and for the requirement A, we want to make sure that all the 3 flows can be offload in hardware. So if we are doing partial offload, like offload flow number 1, flow number 2, but not connection tracking offload, then the performance is the same as the doing everything in software. So if we cannot meet requirement A, then we want to have requirement B, which is do everything in software, but it should be fast. So one proposed solution 1 is to use kernel data path with TC flower. So this people have been using this for a while. So the pros is that TC flower today has more features there. So it supports both tunnel and connection tracking offload into the hardware. And using TC has much better integration with Linux kernel because like all the Linux distribution has TC support. So even if a hardware doesn't is not there, so we can always fall back into the TC or OVS kernel. However, one problem is that if the requirement A cannot be met, so for example, if connection tracking doesn't support in a particular hardware, or some flow cannot be offload. For example, we are thinking about doing layer 7 processing. So hardware probably couldn't be offload. So the fallback performance will be a little bit lower, so about less than 2 million packets per second, if because we are doing it in kernel or OVS. The solution B is to use OVS DPDK with RT flow offload API. So today RT flow support tunnel in-cap, and tunnel decap is also in a progress. However, the problem is that RT flow doesn't support connection checking yet. And but one benefit of using this is that it has better software fallback performance. So if a particular flow cannot be offloaded into the hardware, we can process it in the user space data path in the OVS DPDK, which still shows around 9 or 10 million packets per second. And today we see more people are testing this OVS DPDK with hardware offload. However, deploying OVS DPDK has a lot of system requirement, and it may not be applicable for all the customers or all the environment. So what we are thinking about is to use this third solution, the solution C. So the idea is that if a flow can be processed in hardware, so we want to use user space data path, but instead of using DPDK, we want to use AFXDP. And since we use AFXDP, so we want to use TC Flower to be the offload API, because TC Flower has more features and better integrated into the kernel. And because we are using AFXDP, we also have a chance to do XDP processing in the kernel. So this makes up this 3 layer of processing. So first, imagine we have a flow. So if a flow can be handled in hardware with TC Flower, then we'll do it in hardware. So if not, then second one is we can process in XDP, which is safe and which has pretty good performance. However, it also has its limitations. For example, OVS, first thing to do is to do broadcasting or multicast to flood packet into many ports. So that cannot be done in XDP. If that's the case, then we fall back to OVS user space data path with FXDP, which is still pretty good performance and has less limitations and more flexible in adding new feature or debugging. So with this design, we think that it's better integrated into Linux kernel. It has better fallback performance if hardware cannot be supported. Do it in XDP or in user space. So although each stage will has its limitation, so then we have to have a way to probe, like for a particular flow, which stage we the flow should be done. So we did a pretty early stage of preliminary performance measurement of this design. So first one is, so this is again using like 2 machines and sending a UDP one flow 64-byte UDP packet. So with the hardware offload, like port forwarding between 2 ports, we can get about 31 million packets per second. So this is 25 gig NICAR. And then if we program the hardware to do a little more things, like if we do hardware offload, if we say receive the packet and then encap and v-extend headers and then send it out. So then it shows around 21 million packets per second by doing it in hardware. So if let's say we hit something that cannot be processed in the hardware, then we fall back to the case C, which is XDP. So this is the work done by the Toshiaki, presented in the NetDev conference. So if we do processing in XDP, it shows around 3.5 million packets per second. So here the number is much lower than other XDP benchmark, because actually the code is doing a lot. Like it tries to do the obvious way of parsing packet. It tries to create a compressed compressed data structure of the flow, I call mini flow in the XDP program. So it takes much more cycles to do that. Then if C could not be done in C, then we fall back into the case D, which do the user space data pass with AFXDP. It shows about 4.5 million packets per second. Also, one thing to mention is about the CPU cycles. So for the case of A and B, actually there's no whole CPU cycle being used because it's all done in the hardware. For the case C, it's using one CPU 100%. But for the case D, we are using 2 cores because like AFXDP will use another core, 1 extra core CPU. So summary of the case, the solution C is that we are hoping for the enterprise customer, which they probably don't need a lot of high throughput or packet rate. They can use this obvious user space data pass with AFXDP, but instead of polling mode, they can use interrupt mode, so which will save more CPU, but with lower performance. If they want more performance, then they can enable the polling mode, which will get them better performance than kernel, but use more CPU cycles. But for the high performance like NFV use cases, so with this solution C, we are hoping that they can first try to do hardware offload through the TC Flower, which is fastest because it's all done in hardware and less CPU consumed. And today's TC Flower has much more features. And then if cannot be done, then fall back to XDP or again fall back to the user space data pass with the FXDP polling mode NetDev. So for the future work, today we are still trying to do a couple of experiments to validate how TC Flower offload work with the base. We try pretty basic thing first, like parsing the protocol headers, send the packet to the VM and come back, and we try VXLAN tunnel in cap. So we try to do like basic connection tracking state match on the connection tracking state. But there are still a lot of work to do, like tunnel decap and more connection tracking experiment. That's the hardware flow side. For the obvious XDP processing side, we are looking at the patch sent from the Toshiaki to see how many features can be implemented in the XDP. How many obvious flow requirement flow format can be implemented in the XDP program, and how many limitations are there. And also, definitely, we are looking for more optimization for the AFXDP part. That's my talk. Thank you.
Okay, thank you, William. Let's see if we have any questions for you. Kevin Mason says, how does the performance change when a mix of packet sizes are used for the various configurations?
Probably we didn't have a lot of data there. So today we mostly use like pretty small. So we run 2 cases. So one is to use traffic gen to send 64 byte packet. And another case is we try to run iPerf TCP. Then iPerf TCP triggers more issues. So one issue is that when we are using AFXDP, the checksum of load support is not there. So we are sending bigger packet, but then consume more CPU because we are doing software calculation of the checksum. So, but that's definitely a good question, and we will do that in future work. Yes.
Hey, John says, any idea where the performance difference from AFXDP to DPDK exists?
Oh, yeah. So one thing to mention is that actually the low performance we are reporting from AFXDP is because we divided the number by 2, because we are counting the performance per CPU core. So every time we are doing AFXDP, we use 2 CPU cores. One runs the software RQ daemon, and the other runs the AFXDP user space socket. And when we run OVS DPDK, it only uses 1 core because it doesn't have a driver, right? So that's why the performance looks so gaps, so huge. Yeah.
So are you saying that the actual performance is closer to DPDK?
Yeah, close to, but still we are seeing about at least 10 to 20%. So they are performance overhead. They are also performance overhead of the OVS part. Like OVS has to pre-allocate the UMAN and then fill in the queues. So they are still overhead theirs.
I see.
They're in the OVS driver.
John is asking something I'm curious about too. Is it fair to do that division by 2? Maybe a packet per cycle would be a more accurate measurement to make things fair in 2 cases.
Yes. But yes, I understand. But then the problem is that some of the customers, they care about the how many CPU used by the OVS for the entire system, right? So yeah, so that's why we are doing this.
Okay, we should probably measure this using several sets of metrics and not just focus purely on any of these specific domains, like how many CPUs or how many cycles are consumed. Because from what you say, it sounds like it's a multi-dimensional concern that customers have. They want to know how much CPU usage, how fast their packets can be processed with an OVS, given OVS configuration, and how many cores get used by a given configuration as well. So there's many dimensions to this concern level. And I kind of agree with John. It didn't seem fair to divide the performance by half. It looked a little bit skewed in the graph, and it would lead to questions like John had, like, why is the performance so much lower with AFXDP?
Yes.
Do we have any other questions? Now would be a good time to ask them. We'll give people a couple seconds to start typing, see if we get any of that. No, I don't see anything. William, thank you very much for your presentation. I very much appreciate all your work to try to integrate OVS with various BPF-based networking technologies that we have now. I really appreciate your work. Thank you very much.
Thank you.
Okay, that is the completion of the Networking and BPF Summit for 2020 at LPC. I'd like to thank everyone for coming. In particular, I would like to thank the LPC committee, and I'd like to give specific thanks to Guy, who came in here every day to make sure the channel is working properly, the YouTube stream is operational. I like to thank Elena because she did a lot of the busy work in the background to make this a reality. And honestly speaking, considering the fact that LPC decided to go virtual about 3 or maybe 4 months ago, and we have everything that we saw this week operational and functioning for the most part properly, I think that's quite an accomplishment, and if you see or have a chance to speak with one of the LPC committee members, you should thank them because it's quite an accomplishment. I'd like to also thank the technical committee that we had for networking and BPF Summit this year. That's comprised of myself, Alexei Starowitov, Daniel Borkman, Jakub Sitnitsky, Paolo Benny, Jakub Kaczynski, Michael Kubicek, and Sabrina Dubrotza. All of them worked very hard to review the proposals that led to the presentations you saw this week, so thank them very much. I'd like to thank, in particular, Daniel. He was in the room every day this week, and he did the moderation on Wednesday and Thursday. That helped me a lot. As you know, the conference starts at 7 a.m. in my time zone, and I had to get up around 5 a.m. or so when I would be moderating, and Daniel's helping out, let me sleep in another 30 minutes, so that was so nice of him. I appreciate that. I think things ran very well. I think that the cadence of 4 talks per day was pretty good and didn't overly wear people out. I think any more would have been too much. But if you have any specific feedback about either the Networking and BPF Summit or the LPC in general, please feel free to get in contact with the LPC committee or myself or Daniel to let us know what you think, and we'll make sure we take a look into what your concerns are and try to make this an even better event next year. Once again, thank you everyone for attending. Thanks to all the presenters for their awesome material and lively discussion. I look forward to seeing everyone next year, and thank you very much once again.